Poczekam, aż mi usiądą. Welcome back after another break. Now it's time for a lecture by Tomasz Dudek. Is MLOps tooling the same as DevOps tooling? Enjoy the lecture.
So 1, 2, 3, it works. Perfect. So last talk before the lunch. Is the MLOps tooling the same as the DevOps tooling is the question for today. And as you might have expected, the answer to that is quite complex. And hence this talk. Hopefully afterwards, this will become more clear for you. My name is Tomasz Dudek. I'm a solutions architect at Chaos Gears. I specialize in designing AWS architectures, especially those connected to MLOps and serverless. And here's the agenda for today. We'll start with a quick ML 101, so brief refresher on what machine learning really is. Then we'll discuss why and how to build a MLOps platform. We'll spot the differences and similarities between MLOps and the usual DevOps systems, whatever that means. And finally, as a foreword, we'll discuss how much DevOps is in MLOps and how much machine learning is in MLOps. So let's begin. What is this machine learning all about? Nobody's shocked anymore when I tell them that machine learning is indeed everywhere. Uber tells you how much your ride is going to take. DALL-E 2 generates pictures of so high quality that it makes artists question their future in their industries. Amazon creates shops without cashiers. DeepL has very high quality translations based on machine learning, and something less flashy, such as shops telling you which product to buy next. Each of those features was created as follows. A business person or us or a product owner came with some kind of a problem or a feature in mind. And that feature was connected to cognitive capabilities. So we had to analyze text, analyze music, analyze transactions in our systems, or use computer vision to label something on the images. And we started with tackling that with the usual regular classic code. Obviously, it doesn't work. You cannot, for example, write a program that understands Polish grammar, but in 2022, we are all aware that we can use machine learning for that. So either combining data or giving an environment for the algorithm to play with in form of a training process, an algorithm learns. We either presented the expected answers and it tries to memorize them, or we let it play in some kind of environment, let it play a game of chess and hope that it will learn its rules. And afterwards, the model is trained. So the algorithm is trained, we end up with a model, and that model can be used to solve those tasks. If a task is complex, there's no a single model, there's no one model to rule them all. So just like in the usual programming, if a task is complex, when a problem is complex, we split it into sub-problems that are more manageable, and we can solve those small sub-problems to solve the big one, right? And this is exactly the same case here. For example, if we were a government branch and we had a feature in mind, because we have various forms to file by people that come into the office, for example, to request the ID or a passport. And there's a large form to be filled, and in one of those fields, there's a place to complaints, right? To write some feedback about our office or the government, and we'd like to flag those forms that somebody has written something offensive towards our government. So for example, there's no a single model to solve that, but combining some models would let us solve that problem. So for example, we'll start with a model that only classifies an image and tells us whether that's the correct form or not. Then, if the form is correct, we'll perform the OCR with yet another model that basically moves from the image text to a machine text. Afterwards, we'll use some classic regular code, such as regex, to find that field which contains those complaints. But it turns out there's handwriting involved, so we need to once again translate that into a machine text. And finally, when we've got the machine text, we can then use a model that understands Polish grammar and tell us whether that text was offensive or not. And so the whole complex task was solved, even though there was no single model to solve it. How does a training process look like? Well, a data scientist or a group of data scientists has to pre-process data for the algorithm. It takes many forms. For example, for tabular data, it would mean selecting the right columns, scaling features, joining, adding more data sets, and so on. In terms of computer vision or videos, it's quite different, but in general, it's just processing the data for the algorithm. Then they select an algorithm, they train various models using some CPU or GPU, and finally, when one of those models seems to be ready to be used, they can then use that to produce a great analysis, for example. But how do they use a model? Well, what's a model? A model is, in fact, just a bunch of files. It turns out that deep down below in those algorithms, there are billions. Well, I'm kind of generalizing right now, but let's say in many of those algorithms, there are billions of floating point numbers. And the training process, in essence, is just switching those floating point numbers and looking at the results that the algorithm gives us. If we set up those floating point numbers well, then the algorithm performs well. So a model is those floating point numbers saved onto our disk. But a bunch of files is not yet useful. It doesn't let other people or other applications use a model. So we need to do something about it. And we do that in forms of inference servers. So we wrap that model, this bunch of files into a tiny containerized application that knows how to load those files into a memory, how to use the model library, how to process requests that will eventually come to this container, knows how to log requests and responses, how to collect metrics, and so on. Then, since it's a containerized application, we then create so-called serving layer or a specialized system in our product that basically provides resources for that containerized application to be run. So it provides compute resources, lets others access the model, lets other handles basically the security features, the observability, and so on. How does running a machine learning project looks like? Well, we start with a business goal in mind. The process in general is highly iterative. So we've got a business goal in mind, then we try to frame that business goal into a machine learning problem. If machine learning can be used, then we move on to the data processing part. We create the first model in the phase of model development, but that model is not performing too well, so we move back to the data processing. We add more data sets, build yet another model. That model seems fine, so we move to the deployment phase, to the monitoring phase. For the first month, the model works well, meets the business goal, but after a month, its performance degrades, so we move back to the model development, but since a month has passed, we need to, add that new month of data to the data set, so we're back at the data processing phase, and so on. As you can see, the process is highly iterative. We constantly shift from one phase to another. How a team looks like? Well, there are various roles. I'll skip those well-known to us and only focus on those that might be new for you. We've got data engineers who prepare data for other teams, create data warehouses, data lakes, data meshes, whatever we call them this year. Then we've got data scientists who take that data, pre-process that once again in more machine learning way, and create models, prototypes. Then machine learning engineer takes over, creates those inference servers, and along with a MLOps engineer, work on deploying that model to production. We've got our own culture of engineering as well. Obviously, we've got the MLOps, but essentially it is just DevOps practices applied for machine learning. Yes, there are 3 circles now, so there's design, model development, operations, but its essence is about taking the ownership of what we've built, automating everything, knowing that we are running a production-grade, rock-solid solution, and so on. So the MLOps is essentially DevOps, but in machine learning world. Obviously, it's just a tip of the iceberg, which is what I've typed into one of the algorithms that are very hot recently, because this image was generated by an AI just after I wrote that I want a tip of the iceberg along with the entire long underwater portion of the iceberg. It's a hand-picked example. Some of them were atrocious, but this one looks good. So let's move to the second phase, why and how to build a MLOps platform. So an arbitrary machine learning project looks as follows. We've got two areas, a research lab and a production environment. And those are not silos. I mean, the same team operates in both sides, but each area produces a different result, let's say. Research lab is where the models are produced, trained, the data is processed there, and so on. And afterwards, we've got a model, so we move on to the production environment and deploy that model, monitor, redeploy, and so on. To streamline that process, so as you can see, everything revolves around some kind of machine learning model or multiple models. So to streamline that process, we've got various tools that help us with that. Starting with a place we can explore data in, then some ephemeral clusters that we can train our models and tune them, some experiments tracker in which data scientists save whatever they've been doing with their models. We've got a model registry that we save those models in. We've got a feature store, which is essentially a database for machine learning. We've got model deployment systems, model monitoring, and so on. As you can see, there are various services, and those services are basically applications that we're using to deliver some business value. Why do we need those applications? Well, the answer is quite simple and might sound quite harsh to some of us, because our goal is to build models and solve business problems and not build tools around those models. Basically, we're using some ready-to-use components for training, deployment, and automation. They let us move from scripts, prototypes, and notebooks to something more production grade, let's say. And afterwards, you are not building your own Grafana, Prometheus, Argo, Jenkins, or whatever tools that you're using in your projects. You just take them to build your solution. And this is essentially the same here, only the tools are slightly different because they solve different problems. How do we build such platform? There are 4 options. Well, you can use a software as a service provider. So there are a lot of products in that area that have some of those components that I've listed. You can build it on your own, which I highly discourage, but it's always an option for some companies. You can use open source software, and you can use cloud vendors, because there are various cloud platforms such as AWS and SageMaker, Google Cloud Platforms and Vertex AI, and so on. Here's an arbitrary implementation of that platform. So on the bottom, you see an arbitrary implementation of Kubernetes in AWS. We've got AKS, we've got EC2, so we've got the backbone of the system with some components that basically secure the solution and let us build a multi-account structure in it. And then on top of that Kubernetes, we deploy various applications. As you can see, there are some good old stuff such as Istio, Jagger, Grafana, Argo, Prometheus. Those are example implementations. Obviously, you can switch those for your components. But in essence, because there's going to be a microservice system, they let us tame that system. And then you've got those MLOps components, such as MLflow, Kubeflow, Seldon Core, Feast, Alibi Explain, and so on. And those are those components that I've listed previously. Here's the mapping. So we've got MLflow to track our experiments and to register our models. We've got Kubeflow that lets us explore data, train and tune models, and orchestrate and automate everything around them. We've got a feature store, which, as I said, is kind of like a database, or 2 databases, in fact. And Seldon Core lets us monitor and deploy those models. If we looked at the architectural blueprint, there's nothing too fancy happening. Yes, there are hundreds of AWS technologies, but this is only a so-called AWS landing zone. So it's a setup of multi-account, secure, let's say, AWS starter pack with some inventory management built in, with some access and authentication mechanism, with some databases, with some networking services. That's everything on the right, but it's just a background in terms of this topic. And then we've got a multi-account structure. Each account mimics production. So we've got on each account, we've got a VPC defined, and in those VPCs, we've got, well, let's say a dozen or 100 of EC2 machines, each running some kind of application or a mix of those applications on top of them. On the surface, nothing's too fancy happening here, because in reality, it's just Kubernetes running 10 applications in highly availability mode. So business as usual. You've also got those Prometheus, Grafanas, Argos, and everything that you already know from your projects. You've got also infrastructure as code, CI/CD, tests, linters, whatever good practices that you apply in your projects are also here. The EAC and so on wasn't shown on the picture, but you may imagine that it's there. But the surface might be misleading, and hence the idea for this talk. So let's move on to the differences and similarities between the usual systems and those machine learning related. Here's a quick reminder. That's a bird's eye view on the system. Just Kubernetes running some microservices. And here's the first difference. This is a difference that comes in testing. So we feed a data set to an algorithm, and what we end up with is a model. We then write some tests for that model, and generally speaking, the system works perfectly. Then a month passes, and we've got a different data set with more data in it. We then use the same algorithm with those same parameters, same configuration. We train it for the same amount of time, and what we end up with is a model with a wildly different behavior. Because, for example, it learned way better this time. And so what happens is that tests are failing, even though, in fact, there were no code changes at all, right? Because you just run the same pipeline after a month and it failed. The testing is actually quite tricky because what do we exactly have to test? There's no single stable, always true logic available because the models are highly probabilistic. We don't know exactly how will they behave. We only know that they solve the task 80% of the time, for example. So the testing is quite tricky. Yes, we can write unit tests, so we can create some kind of pipeline that tells us, okay, so the data set is formed as follows. We've got those columns. We are using that algorithm with those configurations and so on. But unit tests only tell you when not to deploy a model, right? Because the tests have blown up. You know that, okay, we cannot deploy that model. But when unit tests pass, then you still don't know whether that model actually behaves well or not. There are some techniques such as expectations testing, invariance tests, skills tests. I'm not going to walk you through this because they are quite novel in fact, but this is generally speaking a green area in machine learning because people found out that we've got tests in usual systems, so we should be doing that in machine learning as well. The second difference is in reproducibility. This is quite connected to the previous issue. So the same data set with the same, so we feed a data set to an algorithm, we end up with a model, but a different data set with the same algorithm produces a model with a different behavior. This gets even trickier because the same data set used on the same algorithm, but in a different version, let's say, even with the same parameters, might also produce a model with a different behavior. And it gets even better because the same data set with the same algorithm, with the same combination of parameters, guess what? It might also produce you a model with a different behavior for various reasons. Even because, for example, the first model has trained for a week and the second model trained for an hour, for example. And even though everything looks on the surface the same, you actually did not reproduce whatever your teammate was doing. Yes, we're using Git and we are versioning whatever the hell we're building in those machine learning applications. If we got some internal pipelines, internal packages, excuse me, then we are using Python package index to store them. We are saving our containers into Docker registry or something else. Business as usual. What's more curious is that, as you've seen, we also need to version data because even though you've got the entire code at your disposal, you are not able to reproduce everything. So we use tools such as data version control, or we do that in our data warehouses or data lakes because they allow you for some kind of data versioning and time traveling. But this is a tool that we use to basically store the data set along with the code, because otherwise we are not able to reproduce anything. And additionally, we are using so-called experiments trackers, because as you've seen, even though if we have some code and we have the data set that was used to produce that model, this still is not, this doesn't give you you are not certain that you will reproduce that model. You still need more metadata about the training process itself, because you need to know what kind of architecture was used to build that model. So how many machines were running, how much the training time took, and so on. And so the ML flow is exactly the tool that stores the metadata about each experiment that you used. It has an UI as follows. As you can see, we've got the information about what code was used, what data set was used, what parameters for the algorithm were used, and what did we end up with. So those metrics on the right mean something to people more interested in machine learning. So only that combination allows us to fully reproduce everything, and as you can see, it means way more versioning. The fourth difference is in more pipelines. If we traced a model's lifecycle, we'd start with data-related tasks, so some data preprocessing, then some model building, then tuning a given model or an algorithm, then saving that model into so-called model registry, and then finally we could deploy that onto our production environment, let's say. As you can see, there are some groups of tasks, and as I said, every project is highly iterative. So we are going to be doing that a lot. So what we need is an automation. So we need an automated machine learning aware pipeline. While the production and the deployment tasks in general can utilize our usual CD technologies, because in essence it's only a container redeployment, right? You can do a canary deployment, blue-green deployment, whatever, but an inference server is only a container, so you have to switch the version of the container. What's more curious are those machine learning related tasks, because we need a way to author them in a machine learning friendly way. We don't want to build a lot of boilerplate around, we just want to specify which steps are done to build our model. And so we are using technologies that let us author those workflows in more machine learning-y friendly way, let's say. Yes, you can also do that in GitHub Actions or whatever, and I've seen that in action, and it works, but it basically forces you to write way more code. Those Kubeflow stuff or Kedro or other pipelines in that area basically have a lot of pre-made components that you can use. With 2 lines of code or several lines of code, all your model building deployment is automated. So basically, there's not only a testing pipeline, a deployment pipeline, there's also a model building pipeline, and that's the difference. The fifth one is in metrics and monitoring. So in most systems, we are interested in the uptime of a given service and its resource utilization. So how much CPU, GPU, RAM, disk space, and so on, how's the resource utilization. And we are absolutely doing that as well too here, right? Because we need to be able to know whether that inference server is alive or not. What's more tricky is the fact that a model that's alive does not equal to a model that's useful. Because if we had a house pricing predictor, let's say, so a software that predicts house prices, and at some point, for some reason, it would always tell you that a given house is worth $100,000, no matter what was the house that you asked the price for. So such system would be useful and would make your business go bankrupt if that was your core business, the house price prediction, even though all your metrics would tell you that your system is working wonderfully. It's auto-scaling up and down, it's utilizing the GPUs perfectly, and so on. So we need to do something about it, and this makes me introduce you to the 2 most important concepts called model drift and data drift. A model drift, essentially, simply put, is a rolling metric that you store about the performance of the model. So for example, one day a model predicts a house price, and after a month that price was sold, that house was sold, so you know the true price of that house, and then you send those 2 data points, so the prediction and the ground truth, to the model monitoring system, and then it compares them and gives you some kind of a rolling metric, how well does the model perform. It's not a real-time solution in a way, because you need to wait for the answers, and you sometimes even cannot have a true answer, but in some cases it can work. The data drift is also a curious concept, and it's better to explain that visually. So let's say you've got an HR solution that tells you whether you should interview a DevOps candidate to your company or not. So there's a lot of data, a lot of technologies that a given person knows, and so on. And among those, that data set, you've got a column that tells you how much a given candidate, how many years of experience with Linux a given candidate has. And as you can see, on average, they've got 5 years of experience. Some of them have 7, 8, and nobody had more than 9 years of experience. You train the model, it performs well, so you decide to deploy that on production. And what happens then, curiously, is that the production data that's flowing into your system and its distribution is widely different. So you start to get questions about the candidates that have 10 years of experience, or 12 years of experience, or 14 years of experience, and your model has never seen such data point. It might still behave well, so it may still predict whether a given candidate should be interviewed or not, but you should definitely investigate in that case and basically decide whether the model is actually still performing well or not. So that concept is called a data drift. Obviously, this is only a simplification of that, but this is the idea. So the sixth difference is in getting the application to run. So usually it's mostly the developer's job to optimize the application. Here is basically some tools or techniques and stuff that developers do to run the application if it's not performing too well. And what's different is that in MLOps is the entire team's job to run the model. So we'll start with the fact that we are building those inference servers, and in fact, this is the entire team. Entire team gives some building blocks for that inference server. So data engineers tell you which data and how should you pre-process that. Data scientists tell you which models should be deployed with what combination of parameters. MLOps engineers and machine learning engineers are working together with DevOps engineers to deploy that model. So basically, the entire team is involved into making the app run. Yes, it might be, if there are some performance issue, it might be as easy as just running a different instances and giving it more compute power. But in some cases, the answer or the solution is way more complex. So sometimes the answer is, okay, this algorithm is responding with 1 second of latency, and we cannot allow that, and we cannot optimize the algorithm, so we have to use another one. So we need to use another algorithm that's responding within 100 milliseconds, but has less accuracy, or is generally speaking worse, but responds faster. So sometimes that's the solution to get the app run, so use another model. Sometimes it's even more trickier, so using more lighter optimizer, another batch size, gradient accumulation, checkpointing, lower precision, those are highly data science specific techniques, and this is not a comprehensive list of them, but generally speaking, there's a lot to be done in that area to even deploy that, because the fact that you trained it, okay, that's fine, but we still need to move that somewhere, and that somewhere might require us a lot of work. And the sixth difference is obviously those applications, because suddenly your system is consisting of various microservices that let you explore the data, train the models, track the experiments, orchestrate, automate everything, register those models, and so on. And those applications are for you as a team to basically streamline your model-related process. We'll highlight some of them. So we'll start with the inference servers, because as I said, those are containers that basically entire team is going to build in some way, because they are in essence the way of the deployment of the model. But yes, they are tiny, and yes, there are some pre-made inference servers that you can use, but it's the entire team's job. Additionally, model registries is a curious concept. And on the right, you see a quick refresher of what I've told you at the beginning. There's a research lab and there's a production environment, and what connects those two areas is a model registry. In essence, this isn't anything else than an artifact repository with some metadata that you store along your files. But I think that this component will eventually merge with artifact repositories, because we call them model registries because they store models, but in essence they are no different than artifacts repositories. So various teams produce various artifacts, various models, and they also save it into a model registry. And then we can download them from a model registry and deploy them into our environments. And finally, the automated machine learning aware pipelines. So as I told you, there's no longer going to be a deployment pipeline which takes a container and deploys that somewhere. Well, there is going to be that pipeline, but additionally, we've got those technologies that know machine learning and let us build something way more rapidly to automate the model building phase. There's a lot of similarity still. Let's remember that, because we are running a microservices application. So there's a lot of deployment and redeployment of the applications. There's a lot of up and down, upscaling and downscaling clusters. When we train a model, we suddenly have hundreds of EC2s or, virtual machines running, but basically that's a business as usual. We also observe the usual virtual machine related metrics, the uptime of the system, its logs. We attend on-calls in some systems. We perform A/B testing. We eliminate toil, which is a word from the site reliability engineering book, but we eliminate work that brings little benefits in general and can be automated. We streamline work for others. We have some SLA, SLO, SLEs. There was a talk in the morning about those parameters. We've got the infrastructure as code, CI/CD, scripts, and as Paweł said, security is the last one. So we also maintain the security of the solution. So moving to the wrap up, here's the quick summary. All the usual site reliability engineering is still here, but the difference is that everything revolves around machine learning models. So we've got a lot of components, a lot of services to let us basically tame the model life cycle, to automate that and to build rock solid production. However, as you've seen, the reproducibility is way harder because the same data set and the same model might produce you the same algorithm and the same data set might produce you a different model. You're using more versioning. You also version data and experiments. You've got a model building pipeline. The monitoring is way more complex. You have some so-called model drift and data drift to observe. Testing is unclear how to do it properly, and getting it to run is basically entire team's responsibility. So how different MLOps is from DevOps in reality? Well, the principles of it stay absolutely the same. This is about taking the ownership of what you've built. This is about building rock-solid production-grade systems. It's about automating. It's about observability and all those buzzwords in general. If you don't know DevOps, you can pretty much understand MLOps instantly. What differs is the underlying implementation, because as you've seen, there are many problems that we encounter with versioning, reproducibility, automation. So you've got new tools to tackle those problems. You've got the experiments trackers, model registries, model monitoring concepts, solutions, and so on. So principles the same, implementation quite different. How much machine learning is in MLOps? That's a good question as well. So it depends who you asked, whether you've asked a platform MLOps, unicorn MLOps, a data scientist forced to do MLOps, or a machine learning engineer that learned the cloud. Each person would give you a different answer to that. But in my opinion, in general, you have to learn it eventually. Not become a master of it, but you need to understand what the hell is your team building, right? If you want to help them, you need to understand what machine learning is really about. However, the so-called platform MLOps is an easy way in, because you can join an existing machine learning team, for example, and work on the Kubernetes cluster if there's one, or on some AWS or other clouds landing zone, and slowly learn those machine learning concepts while still supporting your team. But eventually you have to learn it, because otherwise this will not work too well. If you're about to start that journey, never focus on the details, never focus on those technologies that I've shown. Think of the principles, the MLOps principles or the DevOps principles, read them, let them go into your heart and help your team iterate faster. That's basically your goal. Pick up some machine learning basics. That's an important piece of advice as well. Remember that many of the services that you are running are for you. You are not only deploying the model registry and, okay, that's running, okay, enjoy. You are using that. You are deploying that for yourself. The ecosystem of the MLOps is blooming. There's no single winner. There are various platforms, all-in-one solutions, cloud vendors telling you that their solution is the best. But in reality, there's no single winner yet. And don't make silos. If you pick a technology for your team, always consult with everybody that's going to be used, that are going to use that technology, or even consult that with your entire enterprise. And basically, yeah. So otherwise, you're going to make a silo, and you're going to pick a technology for example, for your data scientists that they are going to hate and won't use it, and only you'll all waste a lot of time. So as a forward, MLOps is not about model registries, experiments, trackers, feature stores, training environment. Those are byproducts of a proper engineering culture that facilitates rapid iteration and stable workloads. So instead of checking boxes such as, yes, we've got an experiments tracker, yes, we've got a model registry, yes, we are using that technology, think of the capabilities of your team that you have. So yes, we move from prototype to production in 1 week. Yes, we can create a new version of a model with 1 click. Yes, we know how to reproduce an experiment that we've performed 6 months ago. Those are most important capabilities that you need to have, and not only deploy blindly some technologies and hope it will work. And with that, we can conclude the talk. Thank you very much. And if you wish to see MLOps in action, we've got a free of cost workshop on that called the SageMaker Immersion Day. If you wish to attend that, just contact me directly. That's going to be a full day workshop on AWS, showing you basically the MLOps in action at SageMaker. Any questions?